So we talked about acid rain a little bit, but now I want to talk about it in more depth. So the effects of air pollution on plants, especially sulfuric and nitric acid, have been known in industrial areas since the 1850s. But it wasn't until the 1980s that the deposition of acidic droplets or particles from rain or snow in the atmosphere was recognized as a major issue. And this is called acid rain. Now, rain is normally slightly acidic with a pH of 5.6, but when you start pumping out these industrial emissions that contain things like sulfur dioxide, sulfate, and nitrogen oxides, that'll acidify rain even more. So much so that the pH can crash down to 4 or lower. Ongoing exposure to acid fog or acid rain or acid mist can cause permanent damage to plants, lake ecosystems, and even buildings. So here we have a pH distribution from rain and precipitation droplets in the atmosphere. And we actually see by and large that the pH is pretty low in this part of the United States, where it tends to be higher when you get to the Midwest. Now, what this means is devastation for ecosystems where the precipitation falling is just wreaking havoc on the physical tissues of these plants, but also on buildings as well, especially those that are made out of things like limestone, which are especially susceptible to acid rain because they're highly, highly soluble. We also have these things in cities called heat islands and also dust domes. So heat islands and dust domes occur in cities even without those inversion conditions in the weather. With their low albedo, concrete and brick surfaces in cities absorb a lot of solar energy, making them extremely hot. So you couple a lot of concrete and brick surfaces with a lack of vegetation or water, that results in extremely high amounts of solar energy that is turned into heat. So as a result, temperature in cities is actually frequently about 5 degrees centigrade warmer or 9 degrees Fahrenheit warmer than in the surrounding countryside. We call this phenomenon the urban heat island effect. In addition to that, tall buildings create convective updrafts that sweep pollutants into the air. And stable air masses created by this heat island over the city concentrate pollutants in a dust dome. So not only is it extremely hot, but you also have high concentrations of air pollutants in your cities. And here's a video that does a good job of explaining why that is.
There's a reason that summers in the city are so hot, and it's probably easiest to explain why with thermal vision. It shows the heat all around me and also the coldness of this ice cream cone. Cities are often hotter than their suburbs due to a phenomenon known as the heat island effect. All of that asphalt, concrete, dark rooftops, and tall buildings, they absorb and store heat. And there are a lot of people using a lot of energy, driving cars, riding subways, running the AC. All of these materials and activities either create or retain heat. And all that stored heat causes steeper nighttime highs when people would otherwise have a chance to cool down. The way all these heat storing elements are laid out matters quite a bit. In cities laid out in grids, like Phoenix, Chicago, or Washington, D.C., the buildings are closer together, like closely packed coals in a fire, keeping heat in. More space between buildings creates more circulation. Another way to combat this heat island effect is through green space. Parks, trees, plants, they don't absorb as much heat. They actually send water back into the atmosphere. Between all those hot buildings, that cools things off. Another solution is color. Light colors reflect sunlight back into the atmosphere instead of storing it as heat. It's easiest to see in crosswalks, and it's true for the color of buildings and other urban surfaces too. And one long game way to combat the heat island effect is to avoid using air conditioning when you don't need it. AC uses a ton of electricity and creates a feedback loop. When we get that electricity from coal or natural gas, that puts more carbon dioxide into the atmosphere, which warms the planet, making cities even hotter. But this isn't just about comfort. Today, heat waves kill more people than any other extreme weather event, more than tornadoes, hurricanes, and even floods. City populations keep growing, and those cities are only getting hotter. This is Let's Talk, NPR's News Explained.
All right. So we've only recently realized that pollution affects rural areas as well as cities. Even supposedly pristine places like our national parks are suffering from air pollution. For example, here we have a picture, probably can't even tell what it is. It's Grand Canyon National Park, where maximum visibility used to be about 185 miles. But now it is so smoggy that on some winter days, visitors can't see the opposite rim that's only 12 and a half miles across the canyon. This is because of mining operations, smelters, and power plants, some of which were actually moved to the desert to improve air qualities in the cities, like in LA. Those are the main culprits. Studies indicate, however, that if all human-made sources of air pollution were shut down completely, the air would clear up in just a few days, and there would be about 90 miles of visibility nearly everywhere, rather than the about 15 kilometers that we have been accustomed to recently. Recent studies have found that rural sources also impact urban areas. In some part of LA, for example, ammonia that drifts from nearby dairy feedlots causes as much smog in LA as cars in LA do. And finally, huge regions are affected by pollution. A gigantic, quote unquote, haze blob, as much as 2,000 miles across, covers most of the US and the eastern part in the summer. That can cause a reduction in visibility as much as 80%. So I said that recent studies suggest that if we just stopped our human-caused emissions for a few days, that we would be able to see clearer. And so sort of a natural experiment happened last year with the lockdowns for COVID-19 that allowed us to drastically reduce our emissions and see how the environment responded. And scientists have studied the response and quantified it. And here we have a paper that was published in August of last year in the Proceedings of the National Academy of Sciences, titled COVID-19 Lockdowns Cause Global Air Pollution Declines. Isn't that awesome? So here we have two panels of one figure, one that is showing the reduction in particulate matter compared to baseline, and another one showing the reduction of nitrogen oxides compared to baseline. So here the purple colors indicate a reduction in those two types of pollutants relative to a 3-year average baseline that was calculated for the past 3 years, not including 2020. So by and large, we see across Asia, in the United States, and in Europe, we see drastic decreases in the amount of nitrogen oxides produced and particulate matter produced. So all of this comes down to air pollution control. What are the best strategies and ways forward? You may have heard this thing called dilution is a solution to pollution. That is actually very untrue because, as we know, even minute amounts of heavily toxic things are dangerous, like mercury and lead. So no, dilution is not the solution to pollution. Tall smokestacks were built to send emissions far from the source where they can become difficult to detect or trace back to their source. And in the 1980s, President Reagan decided to help solve pollution by building taller smokestacks. Needless to say, that did not work. So with increasing global industrialization, dilution is no longer an effective strategy. So what is an effective strategy. Believe it or not, the best strategy is just reducing production. The best strategy is reducing production of pollutants. And in this way, pollutants can be captured from effluent after burning, and also we're putting out less of it. So the first thing here is particulate removal involves filtering air emissions. These filters trap particulates in a mesh of cotton cloth, spun glass fibers, or asbestos cellulose. These industrial filters are generally just really, really big bags that can be huge, about 10 to 15 meters long and 2 to 3 meters wide. In power plants, they use something called electrostatic precipitators. These are the most common particulate control. They work by sucking up ash particles through electrostatic surface charges, and then they can precipitate or collect these particles and then either reuse them or they can throw them away in a safe manner. We also have sulfur removal that's important because sulfur oxides are among the most damaging of all pollutants in terms of human health. Switching from soft coal with high sulfur content to low sulfur coal, like what is used at the Kingston fossil plant, is the surest way to reduce sulfur emissions. In addition, we have those nitrogen oxides. These can be reduced both in internal combustion engines and industrial boilers by as much as 50%, simply by carefully controlling the flow of air and fuel. Stage burners, for example, control burning temperatures and oxygen flow to prevent the formation of nitrogen oxides. And the catalytic converter on your car uses platinum, palladium, and rhodium catalysts to remove up to 90% of those nitrogen oxides that are created, as well as carbon monoxide and hydrocarbons. And finally, hydrocarbon controls mainly involve complete combustion or the control of evaporation. Hydrocarbons and volatile organic compounds are produced, remember, by the incomplete combustion of fuels. So if we simply do complete combustion or control the evaporation of those hydrocarbons, we can effectively control the emission of those hydrocarbons and prevent the escape of fugitive gases from those sources. Here we have that electrostatic precipitator that we talked about on the previous slide. These precipitators can remove up to 99% of unburned particles in the smoke from power plant emissions. These electrodes, they transfer a charge to the particles that pass through. So smoke particles will pass through, they'll become charged, and then they're going to adhere to these collector plates. Those plates are then shaken and the particles are shaken off, and we call that fly ash. That fly ash can be stored in a silo or can be reused later. So clean air legislation in the United States is controversial, but it's actually extremely successful. In the United States, the Clean Air Act of 1963 was the first national law for air enforcement. Because this approach was uneven and difficult to enforce, the act was largely rewritten in the year 1970 through amendments. And these amendments identified the criteria pollutants that we discussed at the top of this lecture. Within those 1970 amendments, rules were also established for standards that are intended to protect human health. Those are primary standards. They also included in those amendments secondary standards to protect materials, crops, climate, visibility, and personal comfort. So a whole lot happened in the 1970 Clean Air Act amendments. The 1990 amendments included major changes in incentives, as well as rules for additional pollutants. That included the ozone depleting CFCs, as well as chloroform, benzene, and other hazardous air pollutants. The 1990 amendments also provided incentives and rules to support the development of alternative fuels and technology. These amendments also finally established rules that allowed the EPA the right to fine violators of air pollution standards. These revisions also created new incentives for pollution control. One of these is a market-based, quote, cap and trade system. In this cap and trade approach, the EPA sets maximum emission levels for pollutants. Facilities can then buy and sell emission credits or permitted allotments of pollutants. Companies can decide for themselves if it's cheaper to install pollution control equipment or to simply buy someone else's credits. So we call this cap and trade, and it has worked well for sulfur dioxide. And when trading began in the 1990s, economists estimated that eliminating 10 million tons of sulfur dioxide would cost about $15 billion per year. So, left to find the most economical way to reduce emissions, utilities have been able to reach clean air goals for 1/10 of that price. A serious shortcoming of the cap and trade approach is that while trading has resulted in overall pollution reduction, there's still some local hotspots that remain where owners have found it cheaper to just pay someone else to reduce pollution than to actually do it themselves. So pollution unfortunately persists in developing areas, including Mexico City, which is a major metropolis area in a developing country, and it has notoriously bad air. The pollution levels in Mexico City exceed the World Health Organization standards in 350 out of 365 days per year. And unfortunately, more than half of all the children in Mexico City have lead levels in their blood high enough to lower the intelligence and retard development. Mexico City's 131,000 industries and 2.5 million vehicles spew out more than 5,000 tons of air pollutants each and every day. And so that's Mexico City. And switching gears to China, they are making efforts to control the pollutants in their air and in their water, but many of China's 400,000 factories have no air pollution controls at all. And that means 7 out of 10 cities in the world with the worst air quality are all located in China. But many places have improved, including Delhi in India. Delhi was once considered one of the world's 10 most polluted cities, but in the 1990s, they really cracked down on how to prevent pollution. That included the addition of catalytic converters. Catalytic converters now, starting from 1990, are required for automobiles, and unleaded gasoline and low sulfur diesel fuels were introduced in the 1990s and continue to be the most popular routes for fuel for automobiles. In the year 2000, private automobiles were required to meet European standards for air quality control. And in the year 2002, more than 80,000 buses, auto rickshaws, and taxis were required to switch from liquid fuels to compressed natural gas. So there are ways to move forward, and many places have improved. So to conclude, air pollution is often the most obvious and widespread type of problem. Health effects of these pollutants include respiratory disease, birth defects, heart attack, cancer, and developmental disabilities in children. Environmental impacts include destruction of stratospheric ozone, poisoning of forests and waters by acid rain, and corrosion of buildings. We have made encouraging progress in controlling air pollution, progress that does have economic benefits as well as those health benefits.